This is part 5 of the recorded lectures for viruses. I'm hoping it will be the last part, but I can't make any promises. But anyway, um, we were going to talk about vaccines and the primary method for controlling viral disease is by vaccination, which is intended to prevent outbreaks by building immunity to a virus or virus family. Um, what you basically have to do to create a vaccine is you have to use something that your immune system will react to. And your immune system can react to live viruses, killed viruses. If they're live viruses, they tend to be viruses that have been um, rendered less dangerous. In other words, they won't cause you to become sick. Um, or even molecular subunits of the virus. Remember how we talked about how viruses can contain glycoproteins, and those glycoproteins can look like spikes on the outside of the virus, and then the glycoproteins must bind with a viral receptor on the host cell. Well, those glycoproteins, just the glycoproteins, can be used as molecular subunits of the virus in order to um, produce a vaccine. Now, if the vaccine is a live vaccine, it's designed in a biological laboratory to cause few symptoms in recipients. And that is the reason why sometimes when you get a vaccine, you do get sick. Most of the time it is, if you get sick at all, it's not really bad, but in rare cases it is. Now, statistically speaking, flu vaccines, for example, do not tend to cause you to be sick. So I know I've even been to the doctor and been told by one of the healthcare workers, I wouldn't get that vaccine if I were you because I got it and I got sick from it. You know, that does occur, but it's very, very low risk. It's a much greater chance that it's going to prevent you from getting the current version of the flu that's going around. Um, so, like it says here, there's a low but significant danger that these viruses will revert to their disease causing form by back mutations. So if a mutation has been designed in the virus by a scientist to cause it to be harmless, then it can always mutate back into its disease-causing form just by natural mutations that occur. And particularly, this is a concern in RNA viruses, like we talked about before. Usually what happens is live vaccines are made by attenuating or weakening the wild type virus. The wild type virus is just the word for disease causing virus. By growing it in the laboratory in tissues or at temperatures different from what the virus is accustomed to in the host. So it won't grow as well in the host as what it does in the laboratory. So why is there a new flu shot every year? This goes back to the fact that influenza and HIV are both RNA viruses, and RNA viruses tend to have higher mutation rates. Um, and so every year there is a flu virus that is the most common flu virus found at that particular year during that year, and that flu virus is used to make the vaccine for that year. Now, sometimes you can use vaccines not just for prevention, but for treatment. Um, and the concept behind that is that if you get the vaccine, it boosts your immunity. Um, Rabies, for example, well, it's not, they don't list it here, but for example, when you get a rabies vaccine after you've already been bitten by a rabid animal, that's the concept behind it, and that's the reason it typically works, is that it boosts your immune system to fight the virus that's already inside of you. Um, there are also antiviral drugs. If you are listening to this, watching this lesson right now, you have probably taken Tamiflu or had a family member that has taken Tamiflu. That's an example of an antiviral drug. So, for most viruses, these drugs inhibit the virus by blocking the actions of one or more of its proteins. It's important that the targeted proteins be encoded by viral genes and that these molecules are not present in a healthy host cell, because if they are present in a healthy host cell, the drug is going to kill your cells as well. So viral growth is inhibited without damaging the host. And here we go. Here's an example, Tamiflu. So what you're looking at in picture A is an influenza virus. And that virus has an enzyme called neuraminidase in its envelope. This is what neuraminidase looks like. And neuraminidase cleaves the connection between viral hemagglutinin, which looks like this. This is the what you're looking at is the glycoprotein spikes that attach to host cell receptors. So neuraminidase cleaves the connection between HA in the viral envelope and the glycoproteins on the host cell surface. In other words, the host cell receptors. Inhibiting NA prevents the virus from detaching from the host cell. And if it can't detach, it can't infect more cells. And Tamiflu is one of those, by the way, it's one of those drugs that you have to take it early on. If you take it early on, it has a very high success rate. If you don't, if you've already had the flu for 24 hours or longer, I'm not sure the exact amount of time, but I know I personally have taken Tamiflu, and I took it very quickly after the onset of my flu symptoms um, a few years back, and I literally went from someone having, I was so weak, I had to be helped onto the table in the doctor's office, um, could barely walk. And I had, my flu symptoms were just really bad. I mean, it came on so quickly. But they prescribed me Tamiflu. My husband drove me to the pharmacy, and I got my prescription filled. And within a couple of hours, I felt almost as good as new. I would say I was back to 80%. So that's one example. There are people who have taken it and gotten no response from it, but it just depends on the situation. All right, anti-HIV drugs. So these are antiviral drugs also, and there are enough of these available today that AIDS is not, or HIV is not, the death sentence that it used to be. When people first started contracting HIV, and then, of course, that led to AIDS, I was a little girl. So I remember that. I remember when HIV, when diagnosis with a positive test for HIV was literally a death sentence. Um, and it is not today, as long as you can get the antiviral drugs. What happens with these drugs is they inhibit the replication cycle of the virus. At multiple phases. In other words, it's kind of like attacking at different stages, hoping that one of the viral drugs will work. So the fusion of the HIV envelope with the plasma membrane, if we can, if there can be a drug that can prevent this fusion, then the virus can't get inside and it can't replicate. If you convert its RNA genome into double-stranded DNA, So if you prevent that, um, reverse transcriptase, integrase, and other viral proteins entering the host cell, if you prevent any of that, then you can prevent the DNA from being formed. And if the DNA is not formed, then you're not going to have transcription, which leads to translation, which leads to proteins being made. And then the integration of the viral DNA into the host genome, you can prevent that. And you can also prevent the processing of viral proteins. So basically, you see 7 different examples here where an antiviral drug can prevent some stage of the viral infection. And by doing so, hopefully keep you from getting sick from the virus. So there we go. All right, now on to coronavirus. So what we're looking at here is a picture. It says SARS-CoV-2. All right, SARS stands for severe acute respiratory syndrome. And this sickness comes from a coronavirus. The coronavirus that is causing COVID-19 is called SARS coronavirus 2, and that's where that comes from. And it's called a coronavirus because the envelope looks like a crown, so that's where the word corona comes from. Okay, so looking at this image, it says binding and viral entry via membrane fusion or endocytosis on interaction of S1 spike glycoprotein with receptor binding protein on membrane receptors. So as you can see, what's happening here is actually receptor mediated endocytosis or fusion, one or the other. But here is the host viral receptor, and then this is the glycoprotein spike S1, and so that attaches to the viral receptor, and somehow the virus enters. And once it enters, it releases its genome, which is a single-stranded positive sense RNA, and that genome begins to produce proteins or enzymes. It begins to produce replicase, and it begins to because remember, transcription doesn't need to happen at all in a single-stranded RNA positive sense virus because it's already messenger RNA. So this already goes into translation because transcription basically does not even have to occur. It's already occurred. All right, so translation is when the messenger RNA produces protein. And what you see is the ribosome from the host cell, and the messenger RNA is being translated into different proteins by the host ribosome. And these are the different, let's see, RNAs that can be transcribed. It says there's nucleocapsid, spike, membrane, and envelope. Okay, so basically, what has to be produced to recreate the virus or to make new virus is the nucleocapsid, the gene for making the spikes, the S1 and S2 spikes, the gene for making the membrane, the gene for making the envelope. And once all of those are produced, then you have the assembly of the mature virion, and then it's released by exocytosis. And I'm going to stop here. We'll have to have one more